Welcome to week 11. This lecture is going to be about the t-test, a new one, for independent means. Now, last week we talked about the t-test, and then in that t-test we gave you this formula that works for the general t-test for sample means when we have just one sample. It also worked when we talked about doing this with two dependent means. What we're going to be doing today is looking at what happens when you have two independent means from a between subjects design. So again, just reviewing what we have covered so far with the t-test is the case where you have just a single sample mean and you want to know if it's different from some population score, or that you have two dependent means from a within subjects or repeated measures design. And there what we did is we just estimated the mean differences between the two conditions to find out whether or not it was significant. But here we're going to have two means that come from two different conditions. So that means that there are different people providing us the different means. So as a result of that, we have to modify this formula for our t-test. So this t-test is called the independent means t-test. It's also known as the two samples t-test, or the mean of, the t-test for independent means. Any variation of that's all the same thing, independent t-test. The hypothesis test that we're going to be using for this particular t-test is that independent groups are going to each have a mean, and we normally are going to assume that their respective population variances are equal, but that we hope to show that the means are significantly different. So even though we have these two groups, these two different conditions, we assume that they have, in their respective populations from which they were drawn, they would have equal population variances, so that the spread would be equal between the two different conditions if we looked at their respective populations. But the reason why we ran the study, it was to show that their means would be different from one another, and that's what the t-test is there for. So the null hypothesis is going to be that there is no effect of the treatment or the experiment or whatever, and so that would mean that the differences between these two means, or the difference between these two means, is zero. So mu1, that's the mean of the first population for the first condition. Mu2 is the mean for the second population or the second condition. And so if we take the difference between those two, it equals zero. And that would be the same thing as just saying that mu1 is equal to mu2, right? Because if they're exactly the same value, there would be no difference between them. So the alternative, or the research hypothesis, particularly when we're talking about a two-tailed test, is that mu1 minus mu2 is not equal to zero. So what we would hope to do is reject the null hypothesis and adopt this alternative hypothesis that the difference between the two means is not equal to zero. All right, so let me first just kind of give you an example study that we're going to be working through today. We'll come back to this later in the lecture and analyze the data, but I wanted just to kind of set up an example of a between subjects design where this independent means t-test would be quite valuable. And this comes from learning the half pipe for a skateboarder. So that what you see there is a half pipe, and the skateboarder is going to learn how to skateboard on that half pipe. And we're not really caring too much about skateboarding itself. What we're caring more about is a theory of learning that's been documented in psychology, that's well supported, that learning and practice that's distributed over a period of time, this is called distributed learning, leads to better retention and performance than if the learning and practice occurs all at once, mass learning, okay? And so we want to just test this theory. We want to say, is it true that if you learn something a little bit over a period of time, rather than trying to cram it all in at once, that you will actually end up doing better on your performance and be able to retain things better? So is it better to practice intensely over a concentrated interval, or to distribute that practice over multiple short intervals when trying to learn to ride the half pipe on a skateboard? So here's an example of one of our lectures in the School of Psychology. This is Phil Grove, and Phil Grove is actually going to show you how you do the half pipe. So he was doing pretty well there until he tried to do that little trick at the end. But anyway, that's what we are looking at in this particular example study. So imagine we have an independent groups t-test, or again, a between subjects design, where 35 people volunteered for the study. 15 people were placed in the distributed learning condition. So what's going to happen to them, these 15 people in group one, is they're going to have distributed learning. They're going to learn how to do the half pipe over 8 one-hour sessions. Okay, so 8 different one-hour sessions. So they end up getting 8 hours of training, but it's sprinkled over a few weeks. The other group are 20 participants that are in a massed learning condition. So these 20 participants have just 2 4-hour sessions. So they're going to cram it all in these 2 4-hour sessions. So we got 15 participants in group 1, 15 people in group 2. Now, and technically, this is actually a quasi-experimental design because the participants chose the condition that they would be in. They weren't randomly assigned to the 2 conditions, but for all intents and purposes, we'll go ahead and treat this like they're independent groups. And again, the independent variable then would be the practice schedule, whether you do this in distributed learning with 8 one-hour sessions or 2 4-hour sessions in the mass learning condition. The dependent variable for this study is the number of repetitions on the half pipe. So as you saw in the video how Phil went back and forth, well, one full back and forth path is considered 1 rep. So we're going to count the number of repetitions at test that they could do. And so they're tested immediately after that 8th hour of practice. So again, we have 35 participants, and we're going to see if this practice makes a difference. Now, I want you to think about how we would analyze these data. And what you can see then is we have 2 conditions. People are in different conditions. And each condition then becomes a sample. And that sample then supposedly represents a theoretical population. And the theoretical population would be like all the people who could possibly be in the distributed learning condition and all the people that could be in the mass learning condition. And then we just happen to pick some people from that population of distributed learning and some people from the mass learning to test in our experiment. So that's the theory behind the statistical test. Or another way to look at it here in this drawing is you can see we've got 2 populations. Population A, this is the population of all the possible reps in the half pipe after mass learning. So that's their number of reps that they did. And then over in the other population, we have the half pipe after distributed learning. And the way that these 2 populations look, you can see they have the same variance. They're drawn to be normal shaped curves with about the same variance, so everything's considered to be equal. But their means are different, such that the mean of the population for B is higher than the mean for population A. So it would look like that on average, people from B are doing better than people from A, right? So what we would do then is draw a sample from A, draw a sample from B, and then we'd have those 2 means, and we'd look at the difference between the 2 means. So that's why I have mean B minus mean A. And that difference between the means, I could plot that. And you can see down in the lower right there that I've got this thing called the distribution of differences between means, which we'll come back to in a moment. But imagine that I just go ahead and do this an infinite number of times, where I keep drawing a sample from A, a sample from B, find the difference between the 2 sample means, and then plot it, and do that over and over and over again. And I end up getting this new kind of distribution, a distribution of differences between means. Okay? So in this case, what you can see is that the mean of this distribution of differences between means is greater than 0. So what would happen overall is that we should start to get more sample means that are greater than for B that are greater than the sample means for A. And that's why we would start to say that we had an effect where distributed learning was leading to more reps. And so therefore, we don't have the same means for the 2 populations. So that's one way this could come out. Another way it could come out is just the opposite. It could be that mass learning is what actually makes the difference. And people do better cramming than distributed learning. So now I've drawn it. So again, they have the same population variances. They're both normal curves. But the mean for A for the population is greater than the mean for B's population. And so if I was going to go ahead and create a sampling distribution from that, I could draw out a sample from A, a sample from B, find their means, find the differences between their 2 means, and plot it down on the lower left. And just keep doing that an infinite number of times, just randomly grabbing samples from A, sample from B. And what you can see then is that the differences between these means then would be less than 0, because if I have A usually being bigger than B, it's going to cause the differences between those means to be less than 0. And so the mean of that sampling distribution would be less than 0. Now, there's a third possibility. It could be that they are exactly the same population, so it makes no difference whether you do mass learning or distributed learning. So now we have no difference between the population means. They have the same shape, they're both normal curves, no difference between the means. And so as we draw samples from A and from samples from B, and then find out their means, and then find out the differences between the means and create our sampling distribution now at the bottom, you could see that the mean of that distribution of differences between means, if we do this an infinite number of times, would be equal to 0. Okay? So here we're saying there's no difference between distributed learning and mass learning, because anytime you grab two samples out, look at the difference between the two means, overall they're going to cancel each other out, and we just would have the mean of those differences be 0. That, in fact, is what the null hypothesis is saying when we do this independent means t-test. It's saying, hey, those two population means, well, they're right on top of each other, and therefore this sampling distribution, this comparison distribution that we're going to compute, would have a mean of 0 as well. So this is what we're going to be testing against, is looking at a sampling distribution called the distribution of differences between means. We're going to say that if the null hypothesis is true, the mean of that is 0. And then what we have to do is see if our difference between our two means is so great, so different from 0, either above or below, that we could end up rejecting the null hypothesis. So we're going to use the same sort of logic we've used in previous weeks. It's just that we have a slightly different comparison distribution. Now you'll notice we've got a lot of different distributions going on here because we've doubled everything, because we've got two different groups, independent groups. That means that we have two different populations. And then that means that each population, if I go ahead and draw the mean from that population and do that, compute it for a particular sample size and throw it back in again, and do that over and over again, you can see that we'd end up with two different distributions of means. Now, if the sample sizes are the same between the two groups, those are going to be identical distributions of means. But if one of them is bigger than the other, then you know that the shape of the distribution of means could be a bit different from each other. And then the next distribution you see down below that is the distribution of differences between means. That is actually the comparison distribution that we're going to use for this independent means t-test. So we're going to have this new distribution of differences between means. And then finally down below we have our samples. Okay? So those are all the different kinds of comparisons or different things that we're going to be computing as we compute our independent t-test. Well, if I go back and look at the data that we would have collected from this skateboarding practice study, you can see there are the 15 participants for distributed learning on the left, and then we have 20 participants for mass learning on the right, and we can see the number of reps that they completed between the two conditions. Now, again, we are assuming that they have different means because that's why we ran the whole study. We think that perhaps mass learning is not going to do as well as distributed learning. But keep in mind the other thing that we're saying is that they have the same population variances or the same population standard deviations. So even though we think that the means are different, we think they have different population standard deviations. And so we're going to have to estimate what the population variance or population standard deviation is that's in common between the two of them. But the problem is that with two different samples, we could end up getting two different estimates of what the population variance is. That, for instance, you could have group 1 that has a mean of 12.2, and its estimate of the population variance is 25, whereas group 2 comes from this other population that has a mean of 14.4, and its estimate of the population variance is 16. What are we going to do there if we're assuming that overall they have the same population variances, but they're giving us different estimates? Kind of going back to this problem here, I'm assuming up at the top that they have different means, but I think that they have the same spread. And therefore, if everything is, kind of following on from that, that would mean that the distribution of means is going to be different for the two if I have different estimates, and everything else would be thrown off. So what we do is we end up assuming that these two estimates are both, going to be off. And what we're going to do is we're going to pool the estimates together to come up with whatever that variance is for the population up at the top. So those two populations at the top, again, are assumed to have the identical population variance. Because we're working with samples down at the bottom, the samples can give us different estimates of those population variances. So the best thing to do is just pool our two guesses together. So we're going to go ahead and let each sample contribute to an estimate of what the population variance is up at the top. If they're exactly the same sample size, we're going to split the difference between them. We're going to let them both go ahead and estimate what the population variance is and just take the average of the two. If one of them has a bigger sample size, though, than the other one, then we're going to go ahead and weigh it so that the sample that has a bigger sample size has more of a contribution into the population variance. Think about that for a second. Why would we want to have the bigger sample size contribute more to the estimate of whatever the population variance is? Well, the answer is that we know that with bigger sample sizes, we're going to get better and better estimates of the population variance. So if we do have one sample that has a bigger sample size, we know it's got to do a better job of estimating, so we're going to let it have more of an impact or more input into the estimated population variance. So again, assuming that the population variances are equal, what we're going to do is with these different estimates of the population variance, we're going to come up with a pooled estimate of the population variance, or S squared pooled. So you can see there's the formula for S squared pooled. Again, this is just estimating what each population's variance is. We're saying that they have the same variance, but we have two different samples that are giving us two different estimates of the population variance, so we have to pool them together. So you can see we have a little S1 squared there and an S2 squared. Those are the two estimates that we got from the two samples. And then that DF1 over DF total stuff, what that's doing is it's going ahead and allowing us to proportionally contribute each estimate of the population variance from those S squareds. And the rest of the formula of what I have down there tells you how to compute DF1 and DF total. So you can see that DF1 is just the n for the first group minus 1. And the DF2 is the n for the second group minus 1. And then the DF total is going to be the 2 degrees of 2 DFs added together. Okay? So that's the S squared pooled. Now, once we have that S squared pooled, the population variance, then we'll be able to go and do things like figure out what the estimate is of the sampling error. And then we're also going to be able to figure out the standard deviation for our new comparison distribution. So that's why we have to have this S squared pooled, especially if we're going to have two different estimates of whatever the population variance is. So let's go ahead and continue now trying to figure out how we're going to come up with this new T formula, how we're going to put all of this together. So you can see that our comparison distribution here is the distribution of differences between means. That's this new comparison distribution that we use for a t-test for independent means. Its shape is going to be that of a t-distribution at different degrees of freedom. So we're going to use that same table that we used last week, a t-table, and use different degrees of freedom to go ahead and look up the values. We need to know then the mean and the variance or the standard deviation of this new sampling distribution where the null hypothesis is true. So we're looking at that comparison distribution, this distribution of differences between means. We know what its mean is based on the null hypothesis. It's 0. So the mean of the new comparison distribution is supposed to be 0 if the null hypothesis is true. Its standard deviation and variance, though, is going to come from the two standard errors that we get for each group. All right? So I know that's a lot of text there, and you might want to spend some time going back and stopping right now and looking at it again. But let's go ahead and move forward and look at again at these pictures. So what we're ultimately doing is trying to go for that distribution down the lower middle, this distribution of differences between means. In order to get there, though, we're going to have to go ahead and figure out what the standard errors are for each of the two populations. So that's what I have circled in red there, the distribution of means that we got from population 1 and the distribution of means we got from population 2. We want to know what their standard errors are. And then once we have those standard errors, then we can go ahead and figure out the standard deviation of this distribution of differences between means. So how do we figure out the standard error for the distribution of means for Pop 1 and for Pop 2 in this particular example? Well, here's the formulas for those. To compute the standard error for the first population, we're going to take our S squared pooled that we first calculated from the estimate of the two estimates of the population variances, and we're going to take that S squared pooled and divide it by n, so n for the first group. And then we do the same thing for the second one to figure out its standard deviation or its standard error for the second population. We take S squared pooled and divide by n for the second group. So now we have the standard deviation for the two distributions of means. And once we have those, then we can go ahead and figure out the standard deviation for that new comparison distribution down there at the bottom, the distribution of differences between means. So going to the distribution of differences between means, how do we calculate what it is, what its variance and standard deviation is? Well, it's going to be based on the distribution of means that we have going into this. So the variance and the standard deviation of the distribution of differences between means. Here's the formula for the variance. It's called S squared difference because it's telling us what the variance is for this comparison distribution. And you can see what it is. It's the standard error estimate for the first population plus the standard error estimate for the second population. So we add those two together and we end up getting the variance. Sorry, I shouldn't say the standard deviation, but the variance estimate for the first distribution means and the variance estimate for the second distribution means. We add them together and we get the variance estimate for the distribution of differences between means. If I take the square root of that, I now have the standard deviation for the distribution of differences between means. And this is also known as the standard error of the difference. So we had the standard error of the mean, that was the standard deviation for the distribution of means, and now we have the standard error of the difference, which is the standard deviation of this distribution of differences between means. So we're now ready to go ahead and create a new t-formula. And what the new t-formula really ultimately, it'll look a little bit easier than this, but here's kind of what we're doing, which is the same logic we did in last week's t-test. So you can see that, first of all, we've got the differences between the means for our two samples, M1 and M2. And then we're subtracting that from the differences between the means when the null hypothesis is true for mu1 minus mu2. And then that's going to be divided by this comparison distribution standard deviation, or the S difference. Now, because the null hypothesis says that mu1 minus mu2 is equal to 0, we don't really need to write that out up there at the top. And so we can get rid of it and just reduce this down to t is equal to m1 minus m2. So take the mean from the first sample, subtract the mean from the second sample, and then divide that by the standard error of the difference. And then we have our t, and we can go ahead and look up the degrees of freedom of it using the degrees of freedom total, and everything will be able to tell when that we should reject the null hypothesis. I'm going to be taking you through two examples in this lecture of all of the steps of hypothesis testing for this. But again, you might want to review this part of the lecture and go back through this again, just to see if you can understand the basic logic of how we're coming up with this t. Now, moving on, the assumptions of the independent group's t-test. We have to, again, look at some of the assumptions that make it appropriate for us to use the independent group's t-test, or the independent means t-test. First of all, the populations that are normally distributed. So we're assuming, again, that the two populations from which these two samples are drawn are normal shaped. And yes, the central limit theorem can correct for this, because even if they're slightly skewed, it doesn't really matter too much as long as we have big enough sample sizes. But ultimately, we're assuming that the populations are normally distributed. The second thing is that we assume that the variance is the same between the two populations. And again, it's a pretty good assumption as long as it's not in reality that one of the populations has a variance that's like more than 4 times the other, one that's more spread out than the other one. We're assuming they're roughly the same shape or same spread. And so with that spread being about the same, that's why we can go ahead and come up with this S squared pooled estimate. And a third assumption is what's called independence of observations, where we can usually assume this if we're using random sampling and random allocation of the two conditions. So if we've flipped a coin or used a random numbers generator or something to put people in each of the two conditions, then that's considered independence of observations. And so we would met the third assumption then of this independent means t-test. So those are the 3 assumptions. And again, they're talked about a little bit more in the textbook. So let's move on now and talk about how we're going to actually do this with real data. And if you look at table 3 in chapter 8, you'll see that they do a nice job of summarizing the steps for a t-test for independent means. So here are the 5 steps that we've been going through the last few weeks, again apply to just the t-test for independent means. So let's work through the steps first, and then we'll go through some actual examples. So first step, of course, is to restate the question as a research hypothesis and a null hypothesis about the population. So this is where you're going to say things like, the null hypothesis is that mu1 minus mu2 is equal to 0. Okay. Second step is to determine the characteristics of the comparison distribution. So remember, our comparison distribution here is this distribution of the differences between means. So in order to get to that, in order to be able to describe it, we have to take what's been given to us in the problem about each of the samples, do a lot of calculations just to get down to understanding what the distribution of differences between means would look like in this case. So that's why there's so many steps here. We have A, B, C, D, and E, and you can see that, well, first of all, the mean of this comparison distribution is 0, according to the null hypothesis. But figuring out its standard deviation, or its S difference, we first have to go ahead and for each population figure out what its estimate of the population variance is. If it's not given to us, we're going to have to calculate that. The second step is figure the pool estimate of the population variance, because they supposedly have the same population variance, so we have to pool together our two different estimates, and that's what B is showing you, what I've already showed you how to compute S squared pooled. The C step is to figure the variance of each of the distribution of means for these two separate populations. So we're going to take the S squared pooled and divide it by the N for the first group and do the same thing for the second group. And then D is to figure the variance of the distribution of differences between the means. So this is our variance estimate of our comparison distribution, where we add our two variances for the distribution of means together. And then finally, step E is we're going to take the square root of that variance estimate to give us the standard deviation of the distribution of differences between means. So now we know how spread out this comparison distribution is based on S difference. C is to determine its shape. And we know, because we're estimating here population variances again, that because of Gossett, we're going to be using a T distribution that has degrees of freedom total as our degrees of freedom in the table. So all of that has to be done for step 2, which is where the bulk of the calculations go for our t-test for independent means. Step 3 is we need to determine the cutoff sample score on the comparison distribution at which the null hypothesis should be rejected. This is just identical to what we did last week. We're going to use our degrees of freedom total. We're going to figure out what our significance level, and then whether we're doing a 1 or a 2-tailed test. We're going to look up the appropriate cutoff in the t-table, which again is reproduced in this chapter. And if the exact degrees of freedom is not given, use the degrees of freedom below it. Step 4, calculate our t. So we need to know what our sample's score would be like on this comparison distribution. So we need to find a t so we can compare it. So we go ahead and take the differences between our two sample means, divided by the standard deviation of the distribution of differences between means, the S difference. And then that resulting t will then be compared to our cutoff and will help us to then decide whether to reject the null hypothesis. So the same 5 old steps we've had before, and now we're going to go ahead and apply it to some problem data. So we're going to give you some examples here where we can kind of work through these calculations. So here's our problem. We have 2 groups of students, and just they happen to have the names S's and T's. And the S students have received an old-fashioned kind of instruction for their course, and the T students have received some sort of new experimental instruction. And we're looking at their final marks in these courses. So the S students, there's their final marks, and then for the T students who got the new kind of experimental instruction, there are their final marks. And what we want to know is there a significant difference between these students? Do the S students and the T students differ overall and how well they're doing? Okay, so we're going to take that data. Notice that it doesn't give us the mean, doesn't give us the standard deviation. We're going to have to calculate those things because nothing else is in this particular problem. Okay, so this problem really requires a lot of computation. Let's go through our steps for hypothesis testing for a t-test for independent means. We'll start with that first step. Restate the question as a research hypothesis and a null hypothesis about the population. So our population of S students, we'll call them population 1. The population of T students is population 2. And so our null hypothesis is that mu1 is equal to mu2, and our alternative hypothesis is that mu1 is not equal to mu2. Or again, remember we can say that for the null hypothesis, mu1 minus mu2 is equal to 0, and the alternative hypothesis would be that mu1 minus mu2 is not equal to 0. All right, so that's step 1. Step 2 is we need to determine the characteristics of the comparison distribution. Now, its mean is always going to be 0 because the null hypothesis is set up to say there's no difference between the two means. But now we can go ahead and figure out its standard deviation. So we have to go through those 5 different steps to calculate the standard deviation for this comparison distribution. Well, first step is we need to know the variance estimate for each of the 2 groups. So for each population, the population represented by the S group and the population represented by the T group. So I've already started to do some of the calculations here, and you can see that the final mark S group, I've gone ahead and figured out what their sum is. So the sum of all of them is 756, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9 participants in the S group, and we have 9 people in the T group, and there's their total scores added up to 798. And then you can see that the means would be for the first group an 84. So that means the S group got an 84. That's the old-fashioned kind of instruction. And then the T group that got the new experimental instruction, they're over on the lower right. Their mean is 88.67. So all I did was just took that sum total there and divided by 9 to get those two different means. And then the next thing we need to know in order to get our estimate of the variance is we need to go ahead and do x minus m for all of those. So what I'm going to do for the left group, the S group, I'm going to go ahead and take 80 minus 84 and so on. So if I go ahead and do that for everybody, you can see that over on the left, there's all of their differences between their x's and their means. And then for the T group, they have a different mean. So it's 98 minus 88.67. And so you can see we get different x minus m's over there. That represents the ones for the T group. And then what we have to do is square those deviations. So now that we have all those deviations, we can just square them in the next column. And so I've squared them all here. And you can see there, I've summed them up down at the bottom. So the sum of these squared deviations is 456. And the sum for the T group is 340. So that's the SS, the sum of squares for the S group, and SS, the sum of squares for the T group. Okay, so now you have those sums of squares for each group. All we need to do now is divide those by their n minus 1. And remember, there's n, here is 9 for each group. So we're going to go ahead and take n minus 1. So you're going to go ahead and take 456 and divide it by 8. You're going to go ahead and take 340 and divide it by 8. So there we go. There's our variance estimates. I've gone ahead and taken the sums of squares divided by n minus 1. So that's 456 divided by 8, or 57. So our estimate of the population variance from the S group is 57. The estimate from the population for the T group is 42.5. So again, notice that we're assuming that the means would be different. That's the whole point of the S versus the T groups. But we think they have the same population variance. That's an assumption that we're making here. But we're getting two separate estimates of the population variances, then they don't match up. So what we have to do is pool them together to come up with a common estimate of that population variance. So we can go ahead and compute S squared pooled as the next part. So here's S squared pool's formulas. And you can remember, again, what we're going to do is we're going to plug in the variance estimate for the first group and the variance estimate for the second group. And we go ahead and multiply them by their degrees of freedom over their degrees of freedom total. So degrees of freedom for the first group is n1 minus 1. That's 8. Degrees of freedom total is 16. We do the same thing for the second group. Now notice what's happening here is that we've kind of split it evenly. Because they have exactly the same sample sizes, each of them is going to be contributing half of their estimate to the overall S squared pool. So that's what happens. We get 0.5 times 57 plus 0.5 times 42.5. And we add them together, 28.5 plus 21.25, and we end up getting our S squared pooled estimate of 49.75. So that is the estimate of what the population variance is that's common between the two of them. Again, there's a homogeneity of variance assumption here that they have exactly the same population variance. It's the same spread, and that pooled estimate of what that spread is 49.75. Now, we're going to take that pooled estimate, and we're going to go ahead and apply that to each of their respective distribution of the means. So each one has a distribution of the means that could be created from their two populations, and we can go ahead and figure out what the variance is for each of those distribution of means in the next step. And what looks funny here is because the numbers are identical, we're using S squared pooled the same for both, and we have the same n's, we end up getting 5.53 for both. So the 5.53 is the estimate of the variance for the distribution of means for the first population, and 5.53 is the estimate for the variance for the distribution of means for the second population. And then we go ahead and take those two separate estimates of the variance of the distribution of means, and we use that to figure out what the variance is for the distribution of differences between means, our ultimate comparison distribution. So our comparison distribution, again, is the differences between these means. And so to get the variance estimate, its S squared difference is equal to the two estimates of the variances for their respective distribution of means. We can add them together. They're the same one here, 5.53 plus 5.53. That gives us 11.06. So there's our variance estimate of the distribution of differences between means. And then the final step is to figure this out in terms of a standard deviation. So we're just going to take the square root of it, and we take the square root of 11.06, and we get 3.33. So all of that work just for step 2 to figure out its standard deviation. We also know that the shape, again, is that it's going to be the shape of a t distribution with degrees of freedom total in the table. Step 3 is, in our hypothesis testing, is to determine the cutoff sample score on the comparison distribution at which the null hypothesis should be rejected. And so we're going to look up this degrees of freedom total in the table, and that will tell us then what it should be, right? So here, remember, our degrees of freedom total is 16. So let's look it up in the table that's in your book. And if I go down and scan down here, we can see that there's the degrees of freedom total 16. One-tailed tests are the columns on the left, two-tailed tests are the columns on the right. We're going to go ahead and pick a two-tailed test with alpha 0.05, so our p-value less than 0.05, and then it gives us then a cutoff of 2.120, okay? And again, it's a two-tailed test, and so I got plus 2.120 and minus 2.120. So there's our cutoff, okay? So our critical value cutoff is plus or minus 2.12. So now, step 4, we want to go ahead and figure out what RT is. And to do that, we need to know our two means for two samples. And then we're going to divide that by this standard deviation of the distribution of differences between means that we calculated into part E. So going back and looking at that formula, I have my differences between my means, 84 minus 88.68. The S difference was 3.33. So what we end up getting is minus 4.68 over 3.33, and that gives us a t then of minus 1.41. So we get a negative t value, and it's 1.41. And then what we need to do is decide whether or not to reject the null hypothesis by comparing this to our cutoff. And you remember that our cutoff was plus or minus 2.120. So we have plus 2.120 and minus 2.120. Our t was minus 1.41. So because our obtained t does not exceed the cutoff, we're going to retain HO. We're going to not reject the null hypothesis. We're going to say this is inconclusive, right? Or that we cannot reject. And in APA style, you could write a sentence like this, where you could say there is no difference between the two tests. T, and then you can see I have in brackets the degrees of freedom total, 18, is equal to, and then I put what my obtained t was, minus 1.41, comma. Then I have that p less than or p greater than 0.05. And in this case, p is greater than 0.05. It doesn't exceed the cutoff. So I put it as p greater than 0.05. So that's our first example. And we've gone through our first independent means t-test. For the second independent means t-test, we'll go back to our video of Phil doing the half pipe. And remember, our dependent variable in this study is the number of reps, the number of times we go back and forth in once. And all of the participants were tested after their 8th hour of practice, okay? So we're going to go ahead and count up the number of reps for each of the participants. And you can see, again, that I have over on the left the distributed learning. On the right, we have the mass learning. And you can see down below, I've got the mean for the distributed learning group. It was 7.4. The mean for the mass learning was 5.2. So right now, just eyeballing it, it looks like the people in the distributed learning are doing more reps than the people in the mass learning, right? And another way to think of this is, what's the difference between the two means? The difference between the two means is 2.2. So on average, these people in distributed learning are doing 2.2 more reps than the people in the mass learning condition. The other thing I've gone ahead and calculated to save us a little time in computations is the variance for the two groups. So you can see now that over on the left, the variance for distributed learning is 2.4. The variance for mass learning is 2.3. So they have very similar estimates of the population variance. But again, we're going to have to come up with a pooled estimate of the variance. Going back to our little drawings again, we're going to go ahead and work with the assumption that the null hypothesis is true. So there's no difference between the two populations on mass learning and distributed learning. And what we hope to do is find that the difference between our two sample means is so great that we can end up rejecting HO. So it's in past some particular cutoff down there in the lower figure. All right, so let's go through our 5 steps of hypothesis testing for this one. Step 1, restate the question as a research hypothesis and a null hypothesis about the populations. So for population 1, it's called the distributed learning group. Excuse me, population 2 is the mass learning. The differences between the two is 0 for the null hypothesis, and it's not equal to 0 for the alternative hypothesis. Okay, so that's step 1. Step 2 is determine the characteristics of the comparison distribution. Now its mean this distribution of the differences between means, according to the null hypothesis, is 0. We need to go ahead and find its standard deviation though, right? So we're going to go ahead and figure out the standard deviation for our group. Now, what we can tell is that for the first thing we need to know is to know what the estimated population variances are for each sample. Well, they were given to us, so we don't have to actually calculate them. So the 2.4 is the estimated population variance for the distributed learning group, and 2.3 is the estimate of the variance for the population for the mass learning group. So those were given to us. So actually A for the part, this part here, A was already done for us. So we can jump right to B. And so the B is figure the pooled estimate of the population variance. And you can see that we're going to go ahead and plug in the variance estimates from the two samples, but we have to adjust them by their sample sizes or their degrees of freedom. And you can see the degrees of freedom for the first group is 14 because it's 15 minus 1. And the degrees of freedom for the second group is 20 minus 1 or 19. And then that gives us for our degrees of freedom total 33. So I'm going to go ahead and take 14 33s and multiply that by 2.4, 19 over 33 and multiply it by 2.3. And you can see that we're going to go ahead and weigh that second group a little bit more in our estimate of the pooled variance. And so that's why it ends up contributing more to it. So you can see that we get 0.42 times 2.4 plus 0.58 times 2.3. That gives us 1.01 plus 1.33. And overall, it gives us an estimate of 2.34. So that is our estimate of the variance for our populations, S squared pooled. Okay, now that we have that, the S squared pooled, we can go ahead and figure out what the variance would be then for each of these distributions of means. Now keep in mind that our two different distributions of means have different sample sizes. So one distribution means is based on an n of 15, the other distribution means is based on an n of 20. And so we go ahead and take that pooled estimate, S squared pooled, and divide it by each of their respective sample sizes. So for the distributed learning, that would be 2.34 over 15, or 0.16. And then for the mass learning, it's 2.34 over 20, or 0.12. And then we're going to have to go ahead and add those together. So we go ahead and take our variance estimates, 0.16 plus 0.12, and we end up getting the variance of the distribution of the differences between the means, 0.28. For E, we want to figure the standard deviation of the distribution of differences between means, so we just have to take the square root of that 0.28. 0.28, take the square root of it, turns out to be 0.53. So it's the standard deviation of the distribution of differences between means. So all of those steps just to give us basically the denominator for our t-test. And again, the shape is that it's going to be a t-distribution with degrees of freedom total as our degrees that we're going to look up. And so in step 3, we're going to go ahead and determine our cutoff sample score again. And remember here that the degrees of freedom is 33. So what we want to do is go look at our table, and you'll notice that down at the bottom here for degrees of freedom, it starts to jump from 30 to 35 to 40. And on the next page, it even goes into higher values. We had 33, and so the instruction is that you want to go to the next lower level if you don't have it. So as you can see here, if we go to 30 for our degrees of freedom, then that means that our cutoff is for 0.05 two-tailed is 2.043. So that's going to be our cutoff for this particular step. Okay, 2.043. Because again, our degrees of freedom total was 33. We're going to go ahead and go, and since we don't have 33 on this table, we go to the next lower degrees of freedom, which is 30, and then that becomes our cutoff, 2.043. And when in drought, always draw. So go ahead and draw yourself a little t distribution there and say, here's our cutoff, plus 2.043, minus 2.043. Okay. So there's our critical value, plus or minus 2.043. Step 4, go ahead and calculate the t. So you want to go ahead and take our t formula, plugging in our means and our standard deviation of the distribution of differences between the means. So we have 7.4 minus 5.2, or 2.2 reps, divided by 0.53, and that gives us a t then of 4.15. So our obtained t tells us that this difference between the two means is 4.15 away from the middle of the distribution. That's pretty far away. And so in step 5, we have to decide then whether to reject the null hypothesis by comparing our t to the cutoff. And so when we do that, we can see that our t greatly exceeds the cutoff of 0.2043. And so because our obtained t, 4.15, exceeds the cutoff, we're going to reject the HO. And distributed learning, therefore, produced more reps than mass learning. T33 equals 4.15, p less than 0.05. Okay. Or another way to say this in APA style would be that there was a difference between the number of half-pipe repetitions after distributed and mass learning, with more repetitions observed after distributed learning. So yes, practicing 1 hour 8 different times yielded more reps. T33, that's our total degrees of freedom total, is equal to 4.15, and the p is less than 0.05. So we have now completed a second hypothesis test, this time rejecting the HO. All right, we got one last topic to talk about in terms of the independent means t-test, and that is, what about the effect size? So keep in mind that the original formula for Cohen's d for effect size is the difference between the two population means over their population standard deviation. The problem, of course, when we're doing t-tests is that we don't actually know the population standard deviation, we're estimating it. So instead of using the estimate of the population standard deviation from one or the other, we're going to go ahead and use the S pooled. So for our estimated d, figuring out what the d would be for this, we're going to take the difference between our two means, M1 and M2, and divide it by S pooled. Not S squared pooled, mind you, but the S pooled. And so once we do that, we'll have our d, and then we can go ahead and calculate what the effect size is. So let's go ahead and go through our two examples that we just went through with our t-tests. And for the first example, we looked at the S and the T students. And from that problem, what we ended up computing was that the S squared pooled was 49.75. Now keep in mind, we don't want to use S squared pooled when we're computing our d. We want to have S pooled. So in order to get S pooled, we just have to take the square root of it. So 49.75, take the square root of that, it comes out to be 7.05. And so then our estimated d is 84 minus 88.68. So that's the difference between the two means between the S and the T students over 7.05, that estimate of the standard deviation. And that ends up giving us a d of minus 0.66. And if you remember, 0.5 is considered a medium effect size. 0.8 is considered a large effect size. So this is somewhere in the middle of that. So I said that that's a medium to large effect. So it's pretty good. So even though we didn't reject the HO in that study, we weren't able to say there was a significant difference between the two. We can tell that there was a pretty good sized effect. And the problem probably there was that we didn't have enough power. We didn't have enough participants in the study. And since it was underpowered, we couldn't reject the null hypothesis even though we had a medium to large effect size. Because we only had 9 people in each condition. And as I told you last week, we should be shooting for like 60 people in each condition. So that's a greatly underpowered study. Now, what about our other example, the skateboarding instruction? Keep in mind there we had 15 people in one condition, 20 in the other. So it's still a bit underpowered here. But we did end up rejecting the null hypothesis. So that kind of tells us that we probably have a pretty good effect size. Well, to figure that out, we're going to go ahead and take our S squared pool that we got from that problem. That was 2.34. And we go ahead and take the square root of it because we want that to figure out what the S pooled is. And so take the square root of 2.34, it gives us 1.53. Plug that in the denominator for our Cohen's d. So I take 7.4 minus 5.2 over 1.53. And you can see that gives us a d of 1.44. Remember, 0.8 is a large effect size. Here we have a 1.44. So this is a very large effect size. So that is why, in this case, even though we didn't have that many participants, based on regular guidelines, we were able to reject the null because we had such a large effect size. So there really was a big effect of distributed learning over mass learning. Okay, so those are two examples of computing effect sizes, and you would normally do this also every time you go ahead and compute a t. What about power? What about that whole issue about power again that I just brought up? Well, to really figure out how many people you need for each group, you can look in Table 6 in Chapter 8 for the approximate number of participants you would need for 80% power for the t-test for independent means. So there is a table there that you could look at to actually figure out before you run a study what you really do need. And it pretty much matches what we talked about in our workshop last time. Okay, now Table 8.7 or Table 7 in Chapter 8 reviews the three kinds of t-tests that we've had over the last couple lectures. So I just want to quickly sum them up. So we have our three different tests: the single sample t-test, the dependent means t-test, and the independent means test. And you can see how they all differ from one another. So keep in mind that the first feature of the t-test is that the population variance is known. No, none of these t-tests do we know the population variance, so we're always estimating it. The second thing that the single sample t-test says is the population mean is known. Yes, because here what we're doing is we're taking our sample mean and comparing it to some known population mean. So there's a case where you'd have a population mean. The other kinds of tests you can see are no. The number of scores for each participant, 1. The t-test was carried out on different scores, no. The shape of the distribution was a t. The formula for the degrees of freedom is n-1, and there's our formula for t. For the dependent means t-test, again, we didn't know the population variance. We don't know the population mean, but we assume when the null hypothesis is true that there's no differences between the two conditions, so it would be 0. The number of scores that we got from each participant was 2, because remember, it's a within subjects design. The t-test was carried out on those different scores. We used a t-distribution again. The formula for the degrees of freedom was n-1, and again, we used the same formula. The only thing that you could add down there on the bottom is that we were doing it on the different scores rather than on the single sample scores that we had in the single sample t-test. And then today, in this lecture, we talked about the independent means t-test. Again, we didn't know the population variance. We don't know the population mean. We only have one score from each participant, but we ended up having two different groups. We didn't carry out our t-test on different scores because they're different people. The shape of the comparison distribution is again a t. The formula for the degrees of freedom, well, there's one for each of the two groups, and then there's a degrees of freedom total where you add the two of them together. And then we can see that in the bottom, we have pretty much the same formula for the t again. It's just that this time we have a different comparison distribution, so we had to come up with the standard deviation for that comparison distribution or the differences between the means. And so that's how we end up getting our t. Now, in addition to learning how to do an independent t-test by hand, I want to show you how you do it in Jamovi. And this will also give us a chance to look at some of the assumptions that underlie the independent t-test. So here's an example that we'll work through in Jamovi. Suppose that we have 33 students who are taking Dr. Harpo's Psych 1030 lectures. There are two tutors for the class, Anastasia and Bernadette. There are 15 students in Anastasia's tutorials, I'll call that N1, and there are 18 students in Bernadette's tutorials, which I'll call N2. The research question I'm interested in is whether Anastasia or Bernadette is a better tutor, or if it doesn't make much of a difference at all, who's your tutor. Now, in a moment, I'll show you the data for these 33 students. Again, this is all fictional data, but here's what it looks like in terms of histograms. You can see that we get a range of people in Anastasia's class in terms of what percentage they get for a grade at the end of the semester. We went anywhere from 50 up to 90. And then in Bernadette's class, we have a smaller range there of scores, but you can see that most of them were bunched up around 70 to 80 to 75, around there. So the question again is this a difference? Is there really a difference between Anastasia and Bernadette's students? So let's work through the 5 steps of hypothesis testing, assuming alpha 0.05 and a two-tailed test. Right, step 1 is to make statements about populations and parameters. So our first population is going to be the students who take Anastasia's tutes. So we try to imagine the entire population of students who would take Anastasia. Population 2 would be the students who take Bernadette's tutes. So our null hypothesis is there's no real difference between them. So the mu1 for the Anastasia tutes should be equal to the mu2 for Bernadette's tutes. The alternative then would be that they're not equal to each other. There is some difference between Anastasia and Bernadette, so mu1 is not equal to mu2. Step 2 is going to be to determine the characteristics of the comparison distribution. Now we know the comparison distribution follows a t-distribution again because we have to estimate the population standard deviation. It wasn't given to us in the problem. So we'll let that stand. We're going to be using a t-distribution. And everything else, by the way, we can go ahead and have Jamovi compute for us. Step number 3, we do need to determine what our cutoff is going to be. And so we again are choosing a two-tailed test with alpha set at 0.05. So when I set things up in Jamovi, I'll make sure I show that I'm doing a two-tailed test. And again, I only will evaluate my results with alpha at p less than 0.05. But nothing else has to be done at this point because Jamovi is going to do the work. Step 4 is to determine the difference between the sample's means on the comparison's distribution. So I'm looking at the difference between these two sample means on the comparison distribution. So I'm imagining a distribution of differences between means. So I'll use Jamovi to find what that t-value should be and what its probability is. Okay, here are our data from Dr. Chico's class, and you can see that I have 3 variables here. The first variable is an ID variable. So that's just my students here. There are 33 of them. Then I have what their grade is, their final percentage in the course. And finally, the third thing I have as a nominal variable is their tutor, whether it's Anastasia or Bernadette. All right, so there's my data file. So now I'm going to go ahead and analyze this using the independent samples t-test. And so I'll go up here to Analyze, to Analyses, and pick t-tests, and pick Independent Samples t-test. And then you can see I already, again, Jamovi has it all ready for me to go. I need to figure out what's my dependent variable. I'm going to go ahead and identify that as the grade. So I put that in here. Then it wants to know the grouping variable. So that's my independent variable, my variable here, which tutor is it. So I go ahead and copy that down into the grouping variable. And so immediately what's happened here is that I'm now looking at whether or not there is a significant difference in grades between the two tutors. But before I do that, let's go ahead and just click a few more things down here. Let's go ahead and pick mean difference and effect size, and finally descriptives. Okay, now looking over on my results table, you can see that for my dependent variable grade, my student's t statistic is 2.12, the degrees of freedom is 31, and the p-value is 0.043, so just below the 0.05 cutoff. So I would say this is significant. You can also see there that the mean difference between the two conditions is 5.48, so that's the difference in percentage really between Anastasia and Bernadette. You can see my Cohen's d, its effect size is actually quite large, 0.74, just short of being a very large effect size. Down at the bottom, I have my group descriptive, so I can actually see that Anastasia has a mean of 74.5, Bernadette has a mean of 69.1. So yes, they are different, and it's such difference that Anastasia's class is actually doing better than Bernadette's. So this does seem like we really have something going on here, that we do have a significant difference between Anastasia and Bernadette. So we can go ahead and take these numbers now and put them into our final decisions about whether or not we're going to reject the null hypothesis. Step 5, again, will be to decide whether to reject the null hypothesis. If the probability of our t statistic is less than our alpha, we reject HO. If not, we retain it. So what did we just learn? Well, we learned that we had a t that gave us a p-value of 0.04. So it was less than 0.05, which is what our level of significance is. So that would mean that we could reject the null hypothesis. And therefore, we'd write up a statement, something like this, where I say that the mean grade in Anastasia's class was 74.53%, the standard deviation was 9, whereas the mean in Bernadette's class was 69.06%, standard deviation of 5.77. An independent t-test showed that this 5.4% difference between Bernadette and Anastasia's class was significant, comma, t, and then in brackets, again, I have my degrees of freedom here, 31, is equal to 2.12. The p-value, the exact p-value that I got was 0.04, and my effect size, Cohen's d, is equal to 0.74, comma, suggesting that a genuine difference in learning outcomes has occurred, that there is a real difference between Anastasia and Bernadette's tutorials. Okay, now that's how we do that in Jamovi. And as I finish up this lecture, I just want to address something else that's important to think about when we're talking about an independent groups t-test. And first of all, one of those assumptions that we mentioned earlier is that the populations should be assumed to be normally distributed. And that's a pretty okay thing to do. We can assume that a lot of psychology variables are normally distributed. And we also know from the central limit theorem that if you're working with large sample sizes, even that will help, because when we have a large sample size, our distribution of means becomes more normal. So we should be okay. So this is one that we're not particularly worried about, although there is a way for us to test this assumption. The second thing is the independence of the observations. And this is what we are assuming, that the two groups in an independent groups t-test are actually unrelated to each other. They don't have any connection, like that we use, for example, random sampling or random allocation to each of the two conditions. Even if we didn't use random sampling, like if you're using males and females, this will work okay, because as long as we don't think there's any particular connection between any one male and one female in our two groups, that shouldn't be a problem either. That would keep us independent. The third one is what's called homogeneity of variance for the populations. And the idea, again, about this is that, is the population standard deviation or the population variance really the same for both groups? Because you'll notice that the way we set up this entire t-test today was assuming that they shared the same population standard deviation. So that's how we could estimate it from each of their contributions of their own population standard deviation or population variance. But what if we really can't assume that? What if it turned out that the variances or the standard deviations were actually quite different between the two populations? And so we shouldn't be making that particular assumption. So there is a way to handle that. And if we want, what we can do is take that last point there and test that using what's called Welch's test for independent samples in Jamovi. So there's a Welch test that allows us to go ahead and just assume that the population variances are not equal and run our t-test anyway. So it's like a modification that Welch came up with when you can't assume that the variances or the population standard deviations are equal. Basically what it does, I've just put here a couple notes to show you that, for instance, when we're looking at that pooled estimate of the the standard deviation of the difference scores, you can see that it uses a slightly different formula there, where you take the variance estimate for the first sample, the variance estimate for the second sample, divide it by n for each one, and then take the square root of it. But the other key thing is that the degrees of freedom is calculated differently. So we have a different degrees of freedom that will usually be smaller than it is for the regular t-test. So it's a little bit more conservative by using Welch's test, because we are estimating something that's actually different between the two of them. And so you can see this whole formula here is how you'd figure out the degrees of freedom. Again, luckily, you don't have to actually hand calculate a Welch test here in this course. And so instead what I'll do is I'll show you how we would do a Welch test in Jamovi, and then we can compare it to the t-test that we had before. All right, so going back now to these assumptions of the tests. First of all, you can go down here and you can click Assumptions Tests. And this is interesting. It's got these different tests here. So here's the homogeneity test. This is a test that actually will test whether or not you can assume that the population variances or the population standard deviations are equal. I can tick that one and it'll give me that test. And then the other thing I can do is I can tick normality test. And this will actually tell me whether or not I can really assume that the underlying populations are normal. So for the normality test, you can see here it says that I'm using this thing called the Shapiro-Wilk normality test, and it has a W value of 0.91, a p-value of 0.827, and it says a low p-value suggests a violation of the assumption of normality. So the probability of this is actually quite high. There's a very good chance of getting a 0.981. So because this is not below 0.05 or some really low p-value, I can assume then that I don't have that. I'm sorry, that my original population is normally distributed. So I'm not violating the assumption of normality. The other one you can see here is that I have this thing called Levene's homogeneity of variances test. And so this is a common test to see whether or not we can really assume that the population variances are equal given what our sample variances are. And this test also passes, suggesting here that it says a low p-value suggests a violation of it. So if we actually had a significant p, that we meant that we actually violated the assumption of equal variances, and so therefore it wouldn't be appropriate to be using this t-test. There is something else that we can do, which is that we can go ahead and pick this over here and say, pick the Welch's. So Welch's is a way for us. So Welch's allows us to not have to make the assumption that the population variances are equal. So this is just done without even that assumption being made. And even though our test passed here in the sense that it doesn't look like we violated the assumption of equal variances given Levene's test, Welch's will let us actually compute it without making that assumption to begin with. So if you look up at the top now, as soon as I clicked Welch's, I now have two different t statistics. I have students t, so that's the one that's originally done by Gossett, And then we have Welch's T. And so there are the calculations that I showed you about how you could do Welch's T, and you get a different T and you get different degrees of freedom. So you can see that T above was 2.12. Now with Welch's T, it comes out to be 2.03. The degrees of freedom, like I said, is calculated differently. So Welch's T is smaller than the student's T's degrees of freedom. So it's only 23. And therefore, my Welch's test has a p-value of 0.054. It's not below 0.05. So if I used Welch's T, I would not reject the null hypothesis. I would have to retain it and say I don't really have an effect here. You can kind of see, though, if I look over at Cohen's D even changes a bit here because of the way that the population variances can't be assumed to be equal. And Cohen's D is just slightly smaller than the original Cohen's D. It's still a very large effect size. So I think the real issue here is I just don't have enough students in my two groups here. It's a pretty small sample size, and so it's kind of hard then when things are that close, when they're that low, to actually talk about whether or not this is significant. I mean, we can just report the statistic. It's below 0.05 in the original student's T. But this is kind of one of those cases where I wouldn't be very comfortable making a final conclusion about the difference between Anastasia and Bernadette because I don't have a large enough sample size. Okay, so there you saw how we could do some assumption tests, homogeneity test, normality test, and we also ran through Welch's T. So that's all I have for you. And so please go ahead and try to do some more problems and practice this on your own.